All right, so once again, welcome to our webinar we're hosting today here at EMI Twente, where we try to connect the theoretics and the practical applications of membrane autopsies, ultimately to figure out why our membranes are fouling. We have a nice program, at least that's my opinion, where we try to combine the more academic insights of Professor Benes together with the more practical insights of Rick van Lin, one of our research engineers. And hopefully we can, by combining these two worlds, really figure out why it is useful to perform a membrane autopsy in order to fully understand what is happening on a more fundamental level at our membrane surface. As I mentioned, we have two speakers. The initial part is more focusing on the fundamentals and the theoretics behind membrane fouling, which will be given by Professor Dr. Nieck Benes from the University of Twente. Professor Benes has been in the membrane world for a long time, I can say. And he will explain to us what is happening at the membrane surface from a fundamental perspective. And then hopefully also we later on get this theoretical insights coupled to the real world, where we later today on the agenda look at membrane autopsy as a diagnostic tool given by Rick van Lin from EMI Twente. I don't want to take away any more valuable time from you guys, so I want to hand the floor over to Professor Benes to start with the first part of today's webinar.
Thank you, Patrick. I think I shared the screen. I'm not sure if...
Yes, now we can see the full screen.
Yeah. So my apologies. This is always a bit of a hassle. Thank you for the kind of invitation, for giving this presentation. So it's true, I'm in the membrane field for quite a long time. My name is Nieck Benes. I've been actively researching membrane science and technology for a long time, but I'm not really the expert on fouling. So I placed the names of two colleagues on this slide, Antoine Kemperman, who truly is an expert on especially biofouling as a topic, and Rob Lammerting, who is really an expert on fluidics, things happening close to the vicinity of a membrane surface, and they actually are the experts. But I will try to give you my perspective on, let's say, the basics of the fundamentals of membrane fouling. Just to place this in context, what is fouling? Well, I think we all have seen something like this. I hope in your home it's not as bad as this window is. But in general, fouling we see as the accumulation of dirty stuff on some surface. And it depends, of course, on the surface that you have. So here it's a smooth glass window, but it's an environment where it's exposed to, well, dirt which over time accumulates here. And this depends on the characteristics of the surface. So here we have a more rough surface, stones. And here you see all kinds of green stuff emerging. So algae, biofouling. Depends on temperature and all kinds of conditions that this surface is present in. I'm sure also many people know about the black stuff. If you have your washing machine in the container where you put the soap, there's always the black stuff. That's also biofouling. There's many different sources and many different types of fouling. Scaling, so precipitation of not too very soluble salts on the surface. All these things can accumulate at a surface. And the surface can be a membrane. But for membranes, the situation is slightly different as compared to the pictures I've drawn here. So the impression of a membrane process. Now, two aspects that we should keep in mind here. One is that these membranes, they might be porous. It's not necessarily the case. There are, of course, also membranes that do not contain very open pores. But many membranes do, especially in filtration processes like ultrafiltration and microfiltration. There's going to be pores inside the membrane which provide a surface area for dirty things to accumulate, for fouling to accumulate. What is also important is that there is an overall transport. So we have something moving through the membrane, and this movement of the fluid, in this case, causes the transport, very effective transport of foulants towards the surface of the membrane. So this transport through the membrane is actually very important for the characteristics of fouling of these type of devices. We see this here. So it's a relatively old paper where people have looked at the transmembrane pressure, so the pressure difference applied over a membrane as a function of time in a micro where they operate the process at a constant flux, in this case of 30 liters per square meter per hour. And what you can see is over time, this transmembrane pressure has to increase. So you need to apply a larger driving force over the membrane to maintain the same flux. And this is associated with the fact that something is accumulating on the surface or maybe even inside the membrane. And here after, well, let's say 350 hours or so, you can actually see that the slope of this line starts to increase a bit more. So the fouling is becoming more and more substantial in that case. Now, if we look at these data again, so that's what you see in this plot. It's the data at the bottom for 30 liters per square meter per hour. And we see that actually over a period of, let's say, 150 hours, the fouling is not so very substantial, but if you increase slightly the flux through the membrane, if we go from 30 to 40, then the increase in transmembrane pressure over time is much more pronounced. And if we even further increase the flux to 50, then even more change in constant or in pressure difference over the membrane is seen. So this indicates that it's very important how large the transport through these membranes is. Now let's have a look at this in a bit more detail. So here we have on the right-hand side a drawing of a membrane. We are looking at microfiltration in this case, because in microfiltration fluxes are very high. So this transport towards the membrane surface will be very, very high. We can see in this case we have a membrane through which we have only solvent permeating. So that's what we will assume. That's for making our theory a bit simpler to derive. And what we do is we divide up the area close to the membrane into a stagnant film and a well-mixed bulk. So in this well-mixed bulk, everything is well-mixed. There are no concentration gradients. But in this stagnant region, very close to the membrane, it doesn't really exist, but let's assume that it does. This concept seems to work quite well for all kinds of transport processes. In this stagnant film, we can get all kinds of concentration gradients. Now, if we look at the concentration of particles, the profile will appear that looks something like this. So this well-mixed bulk, of course, no concentration gradients. But then in the stagnant film, we do see that the concentration will increase if we move further towards the membrane surface. And the reason for this is that we have something called advection taking place. Advection is when the solvent goes through the membrane, and then together with the solvent, the particles are forced to move towards the surface of the membrane, but they are retained there. They cannot pass through the membrane. So they will accumulate at the membrane surface, and that leads to a higher concentration of the particles close to the membrane. This higher concentration, so the gradient in concentration, will actually lead to a diffusive term. And this diffusive term will lead to a flux going back away from the surface of the membrane towards the bulk. Now, I know most of you will not like equations, but we still have to use some of them just to see how large these effects are. So what you see here is the expression for the flux of the particles, NP, that's the flux of the particles, P denotes the particles. And this comprises two terms. The first term is just simply a diffusive term. It's the law of Fick. So we have a concentration gradient, or actually minus a concentration gradient, multiplied by some sort of diffusion coefficient, a parameter proportionality for the flux. And this describes this transport going away from the surface of the membrane back towards the bulk. The other term on the far right side, Cp times phi v, that is the volumetric flow of the solvent towards the membrane. And if you multiply this with how many particles are inside there, so the concentration of the particles, you get the advective flux of the particles towards the membrane surface. Now, if the membrane retains the particles completely, so if the retention is 100%, then this flux must be zero, because there's no overall transport of these particles taking place. So let's look at what we can do with this expression. So now you see on the left-hand side, you see the same expression as we just saw, but we're going to rewrite it now simply to the expression that you see here. So a simple differential equation, and you can solve this to get the expression that you see here. And this expression gives us something called the concentration polarization modulus. It's the concentration of particles at the wall, so very close to the membrane surface, as compared to the concentration of the particles in the bulk. And what we can see is that it's an exponential function, and this number in between the brackets here is referred to as the Becquerel number. It's a dimensionless number, which essentially is the ratio of advection and diffusion. And this exponential behavior is important because this explains why if we change from 30 to 40 to 50 liters per square meter per hour in the experiments that I've just shown you, we see such a big change in the transmembrane pressure difference. It's because the concentration polarization modulus depends exponentially on this so-called Peclet number. Now, we want to have as little as possible, of course, a concentration polarization, because the higher the concentration of particles will be, more fouling we will most likely encounter. But we don't want to do this by having a lower volumetric flux. We want to have as much as possible solvent going through the membrane. So what we can try to do is change the value of delta, and this delta is the thickness of the stagnant film. Again, it's sort of a mathematical concept, but there is sort of a stagnant region which you can affect by changing, for instance, the extent of steering that you do in your device, or the extent of cross-flow velocity when you have cross-flow velocity taking place over your membrane. Also, you can introduce spacers, and these spacers will affect the flow close to the membrane surface, and thereby they will influence the transport of molecules away from the surface again. And even there are options where you change the surface structure of the membrane, for instance, having corrugations on those, or changing the slip, no slip condition, or maybe even have all kinds of nice other features on the surface that will affect somehow the hydrodynamics very close, the fluid dynamics very close to the surface. All these things will affect the transport of these particles taking place and help to get these particles away from the surface again towards the bulk. But they come at a cost. Every time when you do one of these things more substantially, so if you stir faster or have a higher cross-flow velocity, then this will come at the expense of a higher pressure drop over your total membrane module. So this will essentially just cost you money. So there's a sort of an optimum. You gain from this by lowering the concentration of particles at the surface, but at the same time your electricity bill will go up. Now, the other thing that we are interested in is this diffusion coefficient. So the diffusion coefficient of the particles is also important. How mobile these particles are will determine to a large extent how extensive the concentration polarization will be. So if we look at the system that you see here, these are particles in a liquid solution, then what we see is that these particles are moving, but you should realize that this is not a simple normal diffusion process. It's a Brownian motion. These molecules are, or these particles are forced to move around by the water molecules actually that are colliding against these particles. And we can calculate quite simply how large the corresponding diffusion coefficient is. So these particles, they experience something called Stokes drag. It contains the particle size, the radius of the particle r, it contains the viscosity of the liquid. If we multiply by the thermal energy, then we can rewrite everything and we get this Brownian diffusion coefficient. And this contains all kinds of parameters that we know the values of. We know the value of Kb, Boltzmann constant, we know the temperature, and if we fill in for the radius of the particle half a micron, then we get this diffusion coefficient value that you see here, 10 to the minus 13 square meters per second. And this is really, really small. So for comparison, a gas would be in the order of 10 to the minus 6. Most small molecules in aqueous solution are 10 to the minus 9 as a rule of thumb. So this diffusion coefficient is very, very small. And at the same time, the fluxes, so the other part of the Peclet number, they are very large. So this will lead to a quite low Peclet number. Sorry, to a quite high Peclet number. Now, fortunately, there are other mechanisms as well that affect the motion of particles in such a filtration process. One of these, for instance, is associated with the flow field. So if you have these particles and if they have a substantial size, then they will experience close to the surface of the membrane gradients in the velocity, because there will be a slip condition at the surface of the membrane. Velocity of the fluid will be 0. Further away from the membrane, velocities will be higher. And this gradient in velocity, if the particle is large enough, will lead to different velocities, making a rotation possible of this of these particles. And this will lead to an additional inertial lift effect, which is referred to. So this is especially the case in very dilute solutions. Now, if we go to far more concentrated solutions, then the flow through the concentrated area, where there are a lot of particles present, will be affected by the very presence of the particles. So the particles will have an influence on the flow field, the direction of the flow of the solvent through this sort of concentrated region, and this will actually cause movement of the particles, and this will induce something called shear-induced diffusion. And also this is a transport mechanism that will lead to transport of particles away from the surface of the membrane. Now we can plot these things. It's an old paper. This is an old paper of Davis. He plots this the flux that we expect, the predicted flux for a membrane where there's a cake layer on top of the membrane. And of course, how much cake layer there is depends on the Piclan number again. And if you look at the flux as a function of the particle size for Brownian motion, you see that this flux goes down quite fast. So for small particles, there's still some flux, but if you go to larger particles, then the Brownian motion is very slow and flux is almost zero. If you go to inertial lift, then you see that there's an increase, but you need substantial enough particle size before this effect starts to kick in. And then the third mechanism, the shear induced, that's less steep increase with particle diameter, but it starts at smaller particle sizes. So depending on the particle size that you have, one, maybe two, or all three of these processes might be relevant for the transport back from the membrane surface towards the bulk of the membrane. Now, that would be the case for a cake layer that's on top of the membrane. Of course, there are different situations that you can think of. Traditionally, there are 4 different types of blocking which are very often envisioned for this type of process. There's something called standard blocking, where molecules are on the inside of the pores of the membrane, so thereby reducing the pore size of the membrane. There's complete blocking, where particles cover the entrance to a pore, and thereby the pore is no longer, let's say, accessible for transport taking place. There's intermediate blocking, where not all particles will directly block a pore, but there's a probability that they will do. So then the picture looks slightly different. And then, of course, there's cake filtration. So if you're interested in these type of things, put the reference down at the bottom of the page. There's a very good review on these various models where it's explained how you can describe them. I will just have a look at a bit of detail on 1 or 2 of these models, so we have a bit of a feel for what these models, how these models can be used in practice and what their limitations are especially. Now, what we're interested in is the volumetric flow rate, so the change in what we capture, the V, the volume over time. And in these models, this is related to the expression that you see here. K relates to the structure of the pore, so the pore size, for instance, the porosity, how many pores we have and how large they are essentially. This N0 is the initial number of pores that's present, so the open number of pores initially. And then we have P, the pressure, and we have the number of particles blocking pores, and this depends, of course, on how many particles have been filtered out of the solution. So if you use this expression for any of these blocking mechanisms, then you can get a final expression for the volumetric change over time, the amount of volume that you capture over time. So let's have a look at an example, complete blocking. In this case, if we keep the pressure constant, so P0, then the expression becomes the one that you see here. So the only thing that has changed now is that we have substituted P0 for P, and then we can further simplify this, and what we see is that we have some sort of initial rate, and then we have a term that we subtract, that's a blocking constant KB times a volume that we have accumulated over time. From this, we can solve this expression, right? So it's a differential expression. And again, I don't want to go into the details of the mathematics, but if we do this, then the expression that we get is the one that you see here. And what is particular for this one is that we have an exponent in which we have minus KB times the time. So that's characteristic for this particular type of blocking, this blocking mechanism. If we do the same, but now for intermediate blocking, where there's a probability of the particles that they will block the pores, then we get a similar expression, but it is different. It has a different shape. In this case, there's a natural logarithm of the term which contains the time. So this will have a different shape. And this is for all these 4 blocking mechanisms the case. And if you work it out, and this has been done in this paper, so you can have a look at this if you're more interested, then what you can do is actually use the expression that you see on the top here. So it's a second order derivative of the time with respect to volume. It looks a bit odd, but this is what you can draw as a function of the first derivative of time with respect to volume. And then if you do this, then you can plot this on a log-log plot. And the slope of the data that you have, it should give a linear relation. The slope of this relates to the exponent m that you see here. And this m is characteristic for the different types of blocking mechanisms that exist. So for instance, for standard blocking, this m will be 3/2. And if it's complete blocking, then m would have to be equal to 2 in this case. Now, if we look at some data, so here we see some filtration data where we gather a certain filtrate volume as a function of time. In this case, I've worked out the data for data set 1, the orange data set at the bottom. If you do this, then this is the second derivative with respect to volume, so the second order derivative as a function of the first order derivative. And what you can directly see is that there's a lot of scatter. So it's a very scattered set of data. You can further clean this up, average this, and then what you see is that you get a slope of roughly 1, which would indicate that this is intermediate blocking. But the scatter is very large, so the usability, the usefulness of these models for interpreting data is often quite limited, and there are many, many reasons for this. Mostly it's not only intermediate blocking, but also other mechanisms takes place. The theory for this type of analysis is rather limited, and there are assumptions underlying the theory which certainly not always are valid. Now, what we could do, of course, is go for a more advanced characterization. So that's done here. Here we see two different types of computer models that are used. So the first is something called Eulerian, where you follow the concentration as a function of place and time, in this case in 2 or 3 dimensions. So that's on the left-hand side. On the right-hand side, actually, particles, discrete particles are followed. So there's a flow field, and then there are particles, and then you can look at how this evolves over time. So people look at this with all kinds of models. In Twente, Rob Lammerting especially looks at these things with models, but also mostly with experiments. So he tries to confront these computer models with experimental data. On the left-hand side, you see concentration profiles that are measured in time. This is from all kinds of various analytical techniques that you can use. And on the right-hand side, you see particles actually that are followed in time entering, in this case, a pore of on a microchip. So it's on a very well-defined system where you can have a look at how these particles accumulate and block out these different channels in microchips. Now here is a simulation. This is not from the group of Rob. It's not from Rob Lammerting, but he showed me this once. It looks a bit like a pore, and you see particles going through, but actually it's something else. It's from a paper where people have looked at crowd control. So this is a room actually, and this room has this opening, that's a door, and people are trying to get out of this door. It does resemble, though, a microfiltration process or a filtration process in general. And why this is so relevant? Well, again, this was a simulation, but you can also look at experimental data that's done here in this movie, recorded in Spain, the University of Navarra. And on the left-hand side, you can see that people are going through a door, but they are not very stressed. On the other side, there's a high competitivity, so people really are trying to force themselves towards the entrance. And what you can see is that on the right-hand side, this process takes much more time as compared to the left-hand side. So in analogy with microfiltration, if you would have a higher flux, this might cause the process of how particles are behaving close to open pores to be different. Now, concluding, so not going to go into much more detail on the real aspects of fouling. Fouling simply is very much present in all kinds of membrane processes. So in filtration, we have particles, but if you go to reverse osmosis, you will have salts precipitating on the surface of the membrane. All these membrane processes will suffer from fouling, and very often this fouling is related to all kinds of interrelated effects, which are related to the feed, the process conditions, the membrane properties. All these things are interrelated, and it's very difficult to properly characterize these processes. So if you go, for instance, for filtration experiments, and you can use these microscopic and macroscopic models, but even for very simple filtration processes, simple data sets, it's already difficult to predict what the fouling behavior will be, and the analysis is typically quite complicated. So therefore, other approaches could be very valuable. For instance, looking at what is actually on the surface of your membrane by using autopsy methods. And with this, I would like to thank you for your attention so far. There will be questions, I understand, after the presentation of the second presenter. I will be there to try and answer any questions you might have.
Thank you very much, Nieck, for your very nice insight. And I really like the analog of people leaving a room. So the more pressure you put on things, the harder things get. Which is, I think, also true for doing an autopsy. The harder you press people to do an autopsy, the more difficult it becomes to find the solutions you're looking for, which is also a very nice bridge to the story that Rick will be sharing with us. So Rick is a research engineer working at EMI Twente, who, among other things, also deals a lot with fouled membrane elements and figuring out what has happened to them, but more importantly, how to prevent this and to ultimately clean them again. I believe if you start sharing your screen, then I would be able to put that also on there. And then I'd like to give the floor to you. And indeed, as Nieck mentioned, if you have questions, there's the option to ask questions in the Q&A session, which we will try to answer at the end of the webinar.
All right, thanks. And thanks to Nieck for teaching us all about the mechanisms of fouling. And now I would like to share how a membrane autopsy is a great diagnostic tool to identify what type of fouling has occurred on your membrane, and potentially how to prevent this from happening. So I'm Rick van Lin, Senior Research Engineer at EMI Twente. I've spent many years working hands-on with membrane systems across sectors, from drinking water and wastewater to biotech, pharma, food and beverage. Well, I've conducted countless autopsies to uncover why membranes fail, and also perform application studies, so pilot and lab scale studies, all the way until conceptual full-scale designs, to see how and if membranes perform in real processes. But today, I'd like to share some practical insights that help optimize system performance and reliability using membrane autopsy as a diagnostic tool, hopefully leading to fewer unplanned shutdowns, lower cleaning costs, and a longer membrane lifetime. So let's have a look at the different types of fouling. Generalizing, there are 4 types of fouling in membrane filtration. And as we just learned a lot about fouling mechanisms and how particulate and cake filtration works, let's start with those. So there's particulate fouling, which is a deposition of suspended particles. And these can be silts, clay, irons, oxides, colloidal silica. And these are stabilized by electrostatic interactions. So if your feed water charge balance shifts, for example, due to a change in pH or ionic strength, these particles can aggregate and settle on your membrane. And these can then form bridges between feed spacer channels, creating localized pressure drop zones. Next up, there's organic fouling. This is typically adsorption of dissolved organics, such as humic acids, proteins, oils, surfactants. And these are stabilized by hydrophobic interactions, electrostatic interactions, hydrogen bonds, and leads to a formation of films that promote further fouling and potential biofilm attachment. And this then leads to permeate flux decline, but also the alteration of the surface chemistry, right? So the membrane has a charge, but adhesion of this organics will lead to a different charge of this layer, leading to rejection instability. And this can then also be a substrate for microbial growth. Getting straight into the next one, biofouling, which is bacterial adhesion to surface, which is mediated by extracellular polymeric substances, or EPS. which are polysaccharides, proteins, DNA, lipids, all coming from bioorganisms. And this EPS can form a hydrated gel matrix that protects cells, but also traps nutrients from the feed stream. And the impact hereof is that the pressure drop will increase over your membrane due to, for example, feed spacer clogging. And this biofilm can act as a scaffold that captures particulates and even scaling salts. So this leads to mixed fouling acceleration. So once biofilm is present, everything else will stick more easily. And last but not least, inorganic fouling. Supersaturation of sparingly soluble salts such as calcium carbonate, sulfate, barium sulfate, silica is caused by nucleation at the membrane surface or even within these biofilms we just talked about. And this grows into crystals. Well, this leads to a flux decline and increased salt passage, but also will lead to an increased pressure drop over your module. And can also lead to cleaning difficulty. This depends, of course, on the type of scaling and the crystal type. For example, amorphous silica is, well, it's nearly impossible to remove fully. So why is this whole fouling topic important to talk about? Well, in general, fouling leads to an overall reduction of operational performance. So there's a flux decline since there's lower production capacity, increased solute passage leading to reduced product quality, higher pressure drop leading to uneven flow distribution, localized stress on your membrane. But also this higher pressure drop and flux decline will lead to higher energy consumption and operational cost. So more energy, pumping energy is required to maintain the cross flow and permeate flow. And you will have an increased cleaning frequency. So lower production availability, increased chemical cost, and eventually shortened membrane lifetime, which leads to more replacement cost. And eventually this all leads to more downtime, less reliability. So these small scale fouling mechanisms, they can scale up to big operational problems. And in order to understand the cause of this fouling in your process, it's crucial to determine the right solution. And we think a membrane autopsy will help you find the root cause of fouling in your system and adjust accordingly. So what is a membrane autopsy? So it's a systematic post-operation examination of a membrane element, and with the intention to determine the cause of performance decline. So it starts off with a physical dissection of a membrane and an inspection, and it's combined with several analytical techniques such as microscopy and chemical analyses to identify what foulant is on there, if there's any mechanical damage or chemical attack has occurred. So the purpose is to diagnose the root cause of the failure, provide insights for optimization of your process through different types of cleaning, adaptation of pretreatment, or adjusting operational strategies, and in the end prevent recurrence and extend lifetime of membrane systems. So typical triggers to initiate membrane autopsy are, well, of course, a decline in membrane performance. So if there is an increase in salt passage, reduced permeate flow, increased pressure drop over the membrane. If you observe that there's frequent cleaning failures, meaning membrane is not responding to your typical cleaning, or rapid performance decline after these cleanings. If there's any physical damage indicators, such as sudden changes in permeate water quality, or just a typical end-of-life assessment, if there's a scheduled membrane replacement to check if the membrane's been performing up to the standard. So we've touched upon different types of fouling. Let's dive a bit deeper into different types of scaling or damage, and what typically is the source of this fouling, but also how this shows in the process. So what are the symptoms hereof, and what could be the cause of these types of failure? Again, let's start with particulate fouling. So these are typically silts, clays, corrosion products, gravel, and this often shows in the form of an increased pressure drop over your module or a reduced cross flow. a faster fouling, which then also leads to increased CIP frequency, or mechanical damage, which in the end translates to creases in the membrane or space protrusion. You typically see is the cause hereof is the breakthrough of particles from pre-treatment, right? So a non-proper pre-filtration. But what also happens is that if there's flocculation after your pre-treatment, so there's a pH or charge shift after filtration, which then leads to flocculation and exposes the membrane to high TSS loads. But other typical things such as corrosion in piping or tanks, which then end up in the membrane, or things we've also seen is, for example, intermediate storage. So a concrete basin deteriorating, having gravel being entrained into the membrane. Organic fouling, most often humic acids, surfactants, oils, greases. And this also typically shows reduced permeate flow, slow retention, increased pressure drop, reduced cross-flow, faster fouling, increased CIP frequencies. And this is typically caused by more or less sudden precipitation or attachment of organics to the membrane due to a change in the feed. So either a change in feed concentration while the recovery is the same, leading to oversaturation, causing this to attach to the membrane, but also swings in temperature or pH, causing the organics to come out of solution and then attach to the membrane and form this gel layer, which then also makes the membrane surface charge different. Ineffective CIPs, of course, are often caused, or just simply in a wrong operational regime. So too low cross-flow, too high flux. And then there's biofouling, so bacteria, algae, fungi. And again, symptoms: increased DP, reduced cross-flow, faster fouling, increased CIP frequency. Start to see a pattern here. Often caused by insufficient pre-treatment. So there's typically entrainment of EPS due to poor pre-filtration, or, for example, biological growth in activated carbon pre-treatment. So this activated carbon can become a nursery for biofilms, constantly releasing bacteria or EPS into the feed, which then ends up in your membrane. And then there's also the unfortunate combination of having a high COD feed combined with nitrogen and phosphorus sources, which is then a very nice food source for biofilms to start growing on your membrane. Especially if you have a rough surface texture caused by, for example, scaling. If there's poor hydraulics due to, for example, particulate fouling and leading to dead zones in your membrane. Again, making great breeding grounds for biofilm. And then there's inorganic scaling, which we all know is a huge problem. So calcium carbonate, calcium sulfate, silica, barium sulfate, these are typical salts we then precipitate on your membrane. And these symptoms, well, again, same as with the other types of fouling and scaling. Typically caused by a change in feed concentration. So if your solute concentration is increased while recovery remains the same, you end up in a situation where you get oversaturation by default and start scaling quite heavily. Too high recovery, so removal of too much water leading to oversaturation by default. Having ineffective CIP regimes or wrong anti-scalant. So if you have silica scaling, for example, you need a very, very specific anti-scalant to reduce the probability of this happening. And of course, wrong operational regime. So again, too low cross-flow, too high flux. And in addition to fouling and scaling, there's also another potential cause for membrane failure, which is the chemical attack. Caused by, for example, sodium hypochlorite, chlorine, ozone peroxide, And this will lead to a large drop in retention of solutes, even leading to eventually no retention. And typically this also comes with an increase in flux. And typically this is caused by overdosing of oxidation agents or too strong a CIP, or poor scavenging of reactive agents. So for example, to destruct hypochlorite, typically they add bisulfite dosing. But if this is too low, too low dosing or poor mixing is present in the system, you can still end up with oxidative agents reaching the membrane. But also what I've seen is back diffusion during downtime. So poor process design leading to unintended exposure to oxidants by diffusion of hypochlorite through the system or back through the permeate pores. Important to note is fouling feeds fouling. So the first type of fouling that occurs is rarely the last type of fouling that occurs. So for example, if you have particulate fouling in your membrane, it will lead to reduced cross-flow and formation of dead zones. And this is then a nice opportunity for biofouling to start in these dead zones, and localized scaling can occur there, eventually leading, for example, to spatial protrusion and membrane damage. Or another example is that if there's calcium carbonate precipitation, which will increase surface roughness of your membrane, on which organic acids can absorb and become a feeding ground for biofouling, eventually leading to biofilm colonization. So it's pretty difficult to draw conclusions on the type of fouling based on process indicators such as pressure drop, cross flow, etc. Alone. And therefore, an autopsy is a great tool to see if the chicken or the egg came first, and to adjust your process accordingly. So we've made a selection in analytical methods to investigate membrane failure. And this always starts with a visual and microscopic inspection. So opening up the membrane, looking at it, and seeing if there's a discoloring, if there's deposits on there, if there's creases in the membrane, if there's space protrusion. And this is then information to look into to determine what other analytical methods are needed up next. And typically this the first analysis up next is SEM, so field emission SEM or SEM EDX, to look at scaling, composition, and the morphology thereof. And afterwards we try to look at other things if needed. So we can look at mechanical damage by simple light microscopy or doing a rhodamine dye test to see if it leaches through the membrane. Or look at biofilm and organic foulants, typically just screening using FTIR, which is a very nice indicator of chemical fingerprinting of EPSs, for example. There's also more, let's say, niche methods such as dye staining for protein deposits, looking for significant halogen oxidation by doing a Fujiwara test or XPS or even FTIR, or looking for some unusual deposits or heavy metals using ICP or SEM EDX. So I want to look at two case studies just to give you an impression of so what can happen to a module, but also how we approach this and how a membrane autopsy would look like. So first of all is a one that looks worse than it smelled. This was an RO module used for production of processed water. And so the trigger for the autopsy was a differential pressure alarm. There was a flow rate drop down to 28% of the operational set point. And this came with a low recovery. And manual CAP was performed, but there was only a minor flux recovery. And afterwards, there was a quick drop in performance after the CIP. So inspection, well, you don't have to be a scientist to see that this membrane has gone through a lot. So there was significant scaling, and there were different types of deposits on the membrane. There was discoloring, You can even see some folds in the membrane indicating severe mechanical stress. All over the membrane, there were some oily and gel-like deposits, and even some fibrous material was collected from the feed entry point, and some typical deposits on the membrane. So after sampling the membrane on in different positions and scraping some of the deposits of the membrane and from the feed entry point, we started doing analysis. First off, some SEM EDX was performed, and this indicates serious scaling of several sparingly soluble salts. Mainly iron and manganese salts were deposited on the membrane, but also magnesium, silicium, and calcium deposits, all in very large quantities, up to the point where you couldn't see the membrane underneath the scaling. But apart from the obvious scaling, there was, well, a gooey texture on the membrane as well. So we went for FTIR analysis to see what this oily gel-like deposit, what it was. And there were some very clear fingerprints indicating EPS. So there was C double bond O stretching, which happens in proteins, together with some NH bending, CN stretching, both confirming protein presence, being a strong indicator for biofouling. So this was just a lot of biofouling and then EPS on the membrane. So what we did was we sat down with the customer, showed the outcomes of the autopsy, and went through their entire pre-treatment process and process of RO filtration itself, and came down to several process improvement suggestions. So first off, the pre-treatment. So to reduce iron and manganese problems, ensure that the ozonation, which is being used as a pre-treatment, also oxidizes these metals sufficiently. So correct the pH to suit both iron and manganese removal during oxidation, but also ensure solids removal after oxidation, as these particles after oxidation are typically very fine particles. Look into scaling control. So acid control to pH 6 or 6.5 helps for this high hardness water, but also for silica. And check the anti-scalant, because this monomeric silica requires a specialized silica anti-scalant. And well, for the biofouling, minimize stagnation in tanks. Consider using a biocide ahead of RO and also make sure that there's no oxidants reaching the membrane. And since there was a granulated active carbon pre-treatment, disinfect downstream of this active carbon. So use UV or MF or UF, as this granulated active carbon can become a biofilm nursery. And this tight media filtration might help mitigate STI in bioload. Another fun one was a plant-based protein filtration membrane. It was a UF membrane. So this one doesn't look too bad, but it did smell too bad. Same problems here in production. So differential pressure alarm, flow rate drop, major drop in permeance, and non-effective CIP. And well, this is a very clearly there was a quite large mechanical strain on this membrane. So you can see already that there's sort of a flower pattern on the membrane. So there's this entire membrane was just deformed. So there were significant organic deposits and some discoloring on this module. Folds in the membrane, spacer protrusion, and there were these chunks and deposits of a gel-like substance. So telescoping, spacer protrusion. So this membrane was exposed to very large mechanical stresses. You can see the folds of this membrane. There was a torsion, so you could see that the membrane was sort of twisted. And this all ended up, of course, in having dead zones in production. So localized spots where next to no flow velocity was, and therefore a nice place for this gel-like substance to accumulate in. And then there was this flux decline. So we did some clean water flux tests, and these shows that these gel layers are very prone to compaction. So at operational pressures, the flux would decline rapidly. And just a very quick and delicate cleaning already led to normal clean water flux behavior. So it indicated very good cleanability if hydraulics are in order. So if your membrane is not completely mechanically damaged, then a typical CIP should be able to regain your flux. So here we talked about the membrane selection. So these are food type membranes. So you have typically more options with regards to spacer thickness, which allows for better cleaning, more sort of buffer space for organics to build up before ending up in dead zones. Look at process control. So since there's all of this mechanical strain on the membrane, that indicates that there's superseding of the maximum pressure drop over the membrane. So maybe control on pressure drop instead of velocity, and also take into account the viscosity of your product, since this will also have effect on the strain your membrane will endure. And look at the cleaning regime. So maybe the cleaning type is sufficient, but maybe it's required to do this at a more frequent base. So understanding what's happening inside of your membranes is key to reliable and efficient production. And we feel our membrane autopsy turns data into action. So uncovering root causes and providing solutions to optimize your process, leading to better insights, hopefully great performance and lower cost. So how we typically do a membrane autopsy is we start out with an initial consultation, a short first client contact to identify membrane issues, hypothesize cause of membrane failure, and understand pretreatment and filtration process. And this is then followed up by an autopsy intake form to identify what the membrane has been exposed to, what to expect during autopsy, and what the cause of the failure might be. Then the autopsy starts, so inspection and documentation of external house integrity, presence of particles and deposits on housing, anti-telescoping device conditions, if there is telescoping or space protrusion, what's the integrity of the O-ring, etc. And then the dissection and sampling, so opening up of the membrane, unrolling membrane sheets, identify presence of scaling, foulants, particles, and how it's spread out over the membrane, and take some samples of the deposits, membrane sheets, spacers, and perform analysis. So typically it's FE-SEM or SEM-EDX, used for observing membrane surface of fouling. And this can then be used to identify what elements are precipitated on the surface, but also indicate if additional analytical techniques are required, such as FTIR or mechanical integrity testing. And after this is done, we report our findings in a slide deck, present this to the customer with suggestions to improve membrane lifetime and hopefully improve the process. So if you want to know what's hiding in your membrane, well, feel free to contact us for an autopsy. And with that, I would like to give the floor back to Patrick.
All right. Many thanks, Rick. I want to thank you a lot for sharing this with us. I'm quickly glancing over the questions that were posted during your presentation. One of the questions, Rick, is if it's also possible to test the effect of different CIP programs on the already fouled membrane.
Yeah, so a nice option of doing that is having like small membrane samples, so cutting out different membrane samples and trying different types of CIP on a small scale, and then observing the clean water flux performance before and after these types of cleaning. Yeah, that's for sure an interesting thing to do.
I see another question posted referring to one of the articles that was posted earlier today on our website. on the potential impact if we were to abandon fluorinated polymers to make membranes, for example, PVDF-like membranes.
Yeah.
I think the question here is how polysulfone and polyethersulfone handle oxidizing agents and how that would impact fouling, and I think that's also part of the question, if it's the actual degradation of the active layer. I think the article that was posted on the website today is referring to the degradation of the polysulfone or the polyethersulfone if you bring in strong oxidizing agents. But I can imagine, Rick, from your perspective, it might also affect how such a membrane would behave fouling-wise.
Yes, and also depends on where you come from, right? So typical spiral wound membranes are not, they can't handle these oxidizers anyway. But if you start from these membranes that can handle them, so they typically are used, for example, in these ultrafiltration types of hollow fiber modules. They are often exposed to cleaning with hypochlorite, and so if that capability drops, that will definitely lead to well, a bit of a shift in how to CIP or have a chemically enhanced backwash on these types of membranes, because their hypochlorite is a pretty big well, cleaning agent, let's say, in operation. So that will have a big effect in operations.
Yeah.
Yeah.
One other question is, how do you make sure that the deposit that you collect from the membrane really represents the deposit? Because there could be different kinds of fouling, for example, biofouling, scaling, inorganics, along the length of the membrane, but also on different layers of the spiral wound.
Yeah, so that's indeed a tricky one, because they're sort of intertwined, which you typically see if you have if you scoop this, for example, an organic slimy layer off, this will also have calcium carbonate scaling in there typically, because this acts as a sort of a scaffold for the scaling to start and form in. So in that sense, it's important to sort of play detective and look at the rest of the module and try to figure out what was the first type of scaling that occurred. So if there's serious inorganic scaling, and then there's some of this slime forming on top, it's pretty safe to assume that this scaling was there before the organics deposited on top. But that requires very delicate handling and looking at the membrane, because if you're scraping up off the membrane layer, then yeah, you're not sure where it was, and yeah.
Yeah, I think also you're sampling the element at different locations, right?
Yeah. So looking at like the entire length of the membrane, so the parts, middle parts, concentrate parts, is pretty important to see if this changes over the module and if that's in line with well, the rest of the membrane. Also, let's say outer layer and inner layer of the envelopes.
Then I see one final question. I think you mentioned silica scaling along the lines of presentation. One of the questions is if you have a suggestion to prevent silica scaling, as dedicated silica antiscalants are reported to have very limited effect.
Sorry, I didn't catch that fully.
So if you have any suggestion to prevent the scaling of silica, because one of the people that asked the question reported that the dedicated silica antiscalants have a very limited effect.
Yeah. I wish I could say, yes, here's your answer, but at least to my knowledge, the antiscalant is pretty much all you can do, except for well, accepting a loss in recovery. So if you concentrate less, you'll get less scaling, and other than that, it's just the anti-scalant, unless you want to go all the way up to membrane modification, but that's a whole different topic.
see more questions coming up. So some of the questions are going into a lot of detail, and some of the questions are related to the costs of an autopsy. I think related to the costs, drop us a message and we will respond to you by the end of today's working day with a personalized quotation for your autopsy question. I think there is another question which is also potentially for Professor Benes, because it's related to the best way to prevent fouling. Because if you work at a very high flux, or not too high flux, but also should you go to higher cross flow velocities to prevent fouling, or should you minimize?
Yeah, I see the question. Yes, Benjamin Andries is asking this. So it's difficult to give a general answer to this. So if you go to higher flux, then your peak Claire number goes up. So you need to do something to mitigate this effect, and then a higher cross flow velocity, for instance, could help. But this will come at the cost of higher pressure drop over your module, so a higher energy bill. So it might be that in some situations where you really want to prevent fouling, if there's some sort of tragedy and you need to make drinking water available to people in an area where there has been some sort of disaster, you probably want to run at very low flux to prevent fouling taking place at all. It all depends on the system that you're interested in and the situation that you're interested in. I hope this is a bit of an answer.
All right. I think we have answered nearly all the questions that were posted there. So I want to thank everyone for their attendance. Of course, I want to thank Professor Benes and Rick van Lint for their presentation and sharing their insights with us. I think as we wrap up, if you have any related questions, feel free to drop us a email message. I think Rick's email address and also Nieck's email address were on the slides. We will send out a slide deck of this talk, coupled with the recording that we will make available for people that signed up to the webinar. And I think with that having said, I want to thank you all for attending, and I wish you all a very pleasant day.